Hello and welcome back, everyone. And I'm now pleased to introduce our second session of today, starting with a look at environmental applications with Paula Lightfoot. Paula, over to you, please.
Okay, thank you very much, Lynn. I'm just going to turn my webcam back on as well so you can see me. Right, welcome back, everyone. I hope you're enjoying the webinar. I've certainly enjoyed it. We've got a lot of information from GWAR this morning. I'm going to now talk about some of the ways that Earth observation is being used to help deliver environmental policy across the UK. With a bit of a focus on Copernicus satellites, we will bring in some other examples, such as drones. And as before, if you've got any questions, please type them in the questions panel, and then we'll deal with them at the end. And if you think of any other questions you want to ask GWAR or me about some of the technical stuff that you've heard about already, then feel free to ask those as well. So there's two ways in which satellite Earth observation can help to deliver environmental policy. And we tend to talk quite a lot about data analysis and modelling and some of the more complicated things you can do. But I want to just also mention that one of the simplest ways and very useful ways we can use it is for visualization. So using the imagery in GIS or web mapping systems to support routine operations. So I'm going to start off by talking briefly about that, and then we'll look at some of the analytical methods as well. GWAR's already talked a little bit about some of the different spatial resolutions, so I thought we'd look at what you can and can't see in satellite imagery. This is Sentinel-2 imagery of a place that some of us might be quite familiar with, but I doubt you can recognise where this is. You might be able to see that there's a bit of greenery, so maybe there's a bit of vegetation and a few buildings, but I don't think even my JNCC colleagues could probably tell me where this is until we look at the higher resolution 0.5 metre commercial data, which I will show now. That this is actually, you can see Peterborough Cathedral in the bottom of the image, the cathedral gardens, and then here we've got the JNCC offices as well. So if you go, that's it in the Sentinel-2 10-metre resolution, and here it is in the very high resolution data. So obviously, if you want to see real detail in the imagery of really kind of a fine scale, then Sentinel-2 imagery won't be suitable for that. But there is actually a huge amount that it is useful for, and I'm going to show you some examples. One very useful example, because this is very, very topical, this is in the news quite a lot at the moment, wildfires and their impact. So we can see here some Sentinel-2 imagery of the fire on Saddleworth Moor in Greater Manchester, which was in June 2018. And you can see here it's actually still burning, and there's a bit of smoke in the imagery as well. What you would see in the subsequent data, because there's new data coming in every few days, as long as it's not cloudy, you would see the burnt area, and then in following months you would see it start to regenerate. So you can see all of that at this resolution at 10 metres. We can also see plankton blooms at sea. Here's some really fantastic imagery that was just from June this year of a phytoplankton coccolithophore bloom in the English Channel. You can see it's absolutely huge. It's right off the coast of Cornwall and Devon. It comes around the edge of Cornwall, and was actually one of the largest such blooms that we've ever seen. And that was very, very visible just in the normal multispectral imagery. And we can also see river sediment plumes. So these images of the River Tyne and the Bristol Channel, and these were both taken in periods after there was heavy rain and a lot of flooding. So November 2019 and March 2020, if you remember, it was like really big floods. And you can see the kind of peaty black water coming out of the Tyne and just really muddy brown water coming out of the Severn into the Bristol Channel. And that's something else that you can kind of pick up and monitor in Sentinel-2 imagery. You can even see in the Tyne imagery where it's kind of made a wake around a vessel here, where there's kind of clearer water on the other side. You can see that much detail. You can also see, you can visualize the imagery in different ways, which helps pick out things like vegetation, urban areas and bare ground. So here I've taken some Sentinel-2 imagery of Edinburgh and the Firth and Forth. And instead of using red, green and blue, I've used the near infrared with green and red, and it makes the vegetation really stand out in bright pink, whereas the urban areas are in a grey, and bare ground is in darker colours as well. So you can really visualize the differences. So if you were looking at things like urban expansion, or if looking for bare ground, that's a good way of visualizing it. And then here you can see there's a little animation here of a small area in North Yorkshire, and it's going through the changing seasons. You can see the fields being ploughed, crops sown, harvested again, and then over here, this is a wetland nature reserve, and you can see it's all drying out in summer, then it's a little bit wet, and as it goes through the seasons, it then becomes fully flooded in winter, so it's very dry now. I'll just wait for that to come on to sort of November, and there it is completely flooded. So you can look for change detection in land use and water levels in subsequent images. But as Gwa already said, cloud is a bit of a problem in the Sentinel-2 imagery, and sometimes you can't see much at all. And these are actually not the worst examples I could have chosen. You can at least see the outline of the coast here. This is the east coast of England, so you can kind of see the Holderness coast and East Anglia here, and there's the Wash. But in any one of these images, it's quite likely that the area you might be interested in looking at is under a great big cloud and you can't see it. But luckily with the radar data, the Sentinel-1, it can see through the cloud and you can get data night and day, so you've got much more data available. And although, as Gwa said, it's less intuitive, it's not so familiar to us, but you can use it for visualization. There's quite a few things you can pick out in it. So I'll show you some examples of those now. So this is Sentinel-1 imagery of the city of York. So this bright bit here is York. It's got high backscatter values because it's a city. It's got very topographically complex, so it's high backscatter, it's bright. And then some areas have got low backscatter values. So for example, here, there's an airfield, and so the runway is very flat and smooth, as you would hope. So it's got low backscatter values. It's dark on the map. And I've labelled the rivers, the Wharfe, the Ouse and the Derwent, although you probably can't see them that clearly in this image. I'm going to change it for imagery in February 2020 when we had huge floods, and now you can really see the rivers. They've broken their banks, they're showing up very clearly. So you can use this imagery to visualize flooding. Another thing that stands out really nicely because of the contrast is wind farms, offshore wind farms, and vessels at sea, because the sea, it's flat-ish, it's got low backscatter values, it's dark, whereas the wind farms, they're providing some complexity against a flat surface, so they're standing out very bright in the imagery. And so are these boats here, and then also some of the urban areas on the coast like Felixstowe, and here we've got Clacton-on-Sea. They're showing up very bright as well because they've got greater topographic complexity as a more varied surface for the signal to bounce off. So another example of urban areas, things you can see in them. So the urban areas are more topographically complex. You can see bridges, you can see rivers, docks, airfields, things like that. So you can use it for visualization in that way. And here we've got, you can see the difference in all the agricultural fields because different crops have got different kind of radar signatures. Some are more flat and smooth, so they've got low backscatter values, whereas what we've got here is all the woodland around Sandringham Estate, so that's all very bright because woodland is very complex, so the signal's bouncing off it in all directions. We've got the sea up here, which is very dark, and an airfield, so it's very dark, and this really bright area here is one of those static caravan parks, so again, that's a really bright area on the map. So you can use this to look for change, for detecting coastlines, for example. There's actually a lot that you can do with the radar data, even though it's less familiar to us. I'm just going to give you a case study now just to show how you can really add value to using data for visualization, and that's bringing it into corporate web mapping systems. So EasyMap is one example. It's the Environment Agency's WebGIS application used by 10,000 members of staff and over 3,000 users every day on average. And DEFRA and the Environment Agency are working together at the moment to integrate Sentinel-2 data, so kind of cloud-free mosaic imagery, into EasyMap using the web services from the EO data service. So all those 10,000 members of staff will be able to look at it alongside other spatial data, which could be flood maps, for example, and able to help them plan their daily operations. So it's got the benefit of really frequent, up-to-date data coming into their system. So it can help them do their job of protecting people from flooding, targeting regulatory and enforcement activities, and informing waste crime activities. So loads of different areas of the EA's work. So I'm going to move on now and talk about some of the analytical applications. can't possibly cover every single thing, so this is just a bit of a taster because there are so many possible applications. So some things I thought I would talk about would be habitat mapping and change detection, erosion risk, forest monitoring, species counts, and then some marine examples, so looking at how to record the depth of seabed and seabed habitats, the intertidal extent, detecting vessels at sea, and finally an example of using satellite data for air quality monitoring. So we'll go through all of these now. Habitat mapping. This is one of the kind of earliest, most popular applications for EO data, because people really need national habitat maps. It's got so many uses for like modelling, for informing operations and site assessments. And Natural England made it a priority to develop a method for classifying habitats using Earth observation data and machine learning. And there's a link in these slides to a report that explains how that was done. It uses Sentinel-1 and Sentinel-2 with other ancillary data like weather data, infrastructure like roads and buildings. And it's had 3 different phases. So the first one, Living Maps, they just developed a method, then they scaled it up, produced a draft national habitat map, which has been assessed against ground truth data, and it's got a 78% probability of classification accuracy. You see that varies from one habitat to another. And now they're on phase 3 of the project, refining the modelling process and gathering more habitat data to train the model, because as Gwa already said, the ground truth data is absolutely crucial to making sense of EO data. And this was developed to support agri-environment policy, but it's got loads of other applications like reporting on indicators, assessing SSSI conditions, and biodiversity net gain in the planning system, and planning and implementing nature recovery networks. We have used the Living Map method at JNCC, collaborating with the Northern Ireland Environment Agency to create a map for the whole of Northern Ireland, and that has just in the very recent days been completed. And it's also being done in habitat maps also being created in Scotland. Nature Scot and Space Intelligence are working together to produce a satellite-derived UNIS Level 2 map of Cairngorms National Park. And this is part of a project on natural capital asset index calculations. We've taken the Natural England Living Maps method and applied it in areas all around the world. And just going back to what I was saying earlier about how we have also processed Sentinel-1 and 2 analysis ready data for other places outside the UK. So we've got some examples here like the Turks and Caicos Islands, Montserrat, there's places in Peru and Chile, there's the Falkland Islands. So there's loads of different examples, and there is more coming up all the time. So this method having been developed and it's freely available as the R script, you can then apply it anywhere in the world for, because the Sentinel data is global. It's not just habitats that you can map crops as well. And the Scottish Government-led project is now using Sentinel-1 and Sentinel-2 analysis-ready data, again, together with ancillary data sets to help the modelling process, to produce an up-to-date crop map of Scotland, which then, of course, can be used for agricultural and environmental policymakers and regulatory bodies. So it's an extremely useful product. I also want to mention the Living Wales project. Helena might say more about this in due course. I had to fit it in somewhere, and it does do habitat mapping, but it does so much more than that as well. So I would just say that it's a research project to advance the use of Earth observation in Wales, but also internationally. It's a collaborative project with Welsh Government and Aberystwyth University, but also encouraging input from collaborators outside the UK. And it does generate habitat maps and land cover maps, but there's also all kinds of spatial outputs, such as above ground biomass, which is a proxy for carbon. And it does change detection, like changes in canopy cover. And there's a taxonomy of habitat changes. And it also generates ground truth data for making sense of the EO data. So there's like a citizen science Earth Track app for collecting ground truth data. So it is habitat mapping, but there's a lot more to it. So I would urge you to go and have a look at the website if you'd like more information about any of that. I'm just going to move on now and talk about change detection, because the habitat mapping from EO data is becoming quite well established now, but we also want evidence on what condition the habitats are in and whether that's changing, whether there's any trends that we need to pick out and respond to, whether management at a site is working and having the desired effect. And we can use EO data for this. This is something that this is a much newer area of research. And at JNCC, we've developed a web-based app to use Sentinel-1 and 2 analysis-ready data for change detection. And we're now working with these 4 organisations, so Natural England, Historic Environment Scotland, Nature Scot and Natural Resources Wales, to test this app right now at 8 pilot sites across the UK. And we're getting feedback from end users on how easy it is to use, but also how effective and accurate it is. So is it really identifying parts of their sites that really have changed? And then we're going to take their feedback and use that to inform further development to actually take this proof of concept, scale it up to a national level operational application. And it's intended to be a decision support tool, so it won't tell you what change has happened, where it will just flag up areas that could be interesting to have a closer look at and use your local site knowledge to direct your survey efforts, your management resources more effectively to those areas where it looks like something is going on. So I will show you how that works. Here's a screenshot of the app, and what users can do is apply filters to choose the site they want to look at, whether they want to look at things monthly or seasonally, which index they want to look at. So it uses indices for vegetation or water or leaf moisture or vegetation structure derived from the satellite data. So they choose those. And then it will flag up in purple on this map any polygons whose index value exceeds the mean for that habitat by more than 1 standard deviation. And then you can just see the dates of the imagery used to generate those values. And in the graph, you can see the mean value of the selected polygon. And I don't know if you can see here, there's in September 2019, the vegetation index value, so the whether it's healthy vegetation or not, has absolutely plummeted below the mean. There is by about more than 2 standard deviations. It's very low. And you can see that in the imagery here. So this is the NDVI image thumbnails, the 2 in the middle are from September. And you can now see the actual satellite imagery as well. So it's showing you that the meadow has been mown then. It's a lowland meadow and it has been mown. So of course its vegetation index has dropped. So the app has done its job and flagged that up. So you can then look at the imagery and see, well, why has that happened? You can then also download the data as a CSV or a shapefile if you want to look at it in GIS and do any further analysis. So to show you a couple of examples from it, this is an example of coniferous woodland, and you can see that throughout from 2015 onwards, it's had higher vegetation index values than the mean for all coniferous woodland, quite happily. And then around winter 2018, it suddenly drops and just keeps on dropping. So we look at the imagery, we can see that's it as quite a healthy looking woodland. Then by winter 2018, a lot of it's been chopped down. May 2019, a bit more has been chopped down. And by April 2020, the entire thing has been clear felled. So you can look at the images and see, well, there's a very good reason of why what we're seeing on the graph has happened. And this example is from Shrub Heath. This is from the same SSSI in Scotland. And you can see its vegetation index value is really low in some springs and winters. So I wondered, could it be due to heather burning maybe? But then you look at the imagery, so that's it, quite healthy in September 2015. And in March 2016, no, it has been burnt, it's covered in snow. So that's why its value has dropped down. Back up to healthy imagery again, healthy vegetation again. And then in spring 2020, it's covered in snow again. And the same was true in winter 2017. So in that example, it's not a real change, it's that the site was covered in snow. When the snow melts, the healthy vegetation is still there underneath. So just to emphasize, it's a decision support tool. It flags things up, then you have a look at it and see, well, is it a really meaningful ecological change or not? And in that case, not. So my next example comes from the Environment Agency and shows how you can use Earth observation to detect erosion risk and runoff into water bodies. So this brings together a lot of different types of information, but the ones that we're most interested in is using satellite imagery to predict where bare soil is. So it's looking at where you've got bare soil in conjunction with sloping ground and proximity to a watercourse, that's a recipe for, after rain, that you will get nutrients or you'll get chemicals running off the soil into the water. And they have got this app which analyzes Sentinel-2 satellite data for the probability of bare ground, and this helps the Environment Agency's officers to target field visits to where they think there is a water pollution risk because there's bare ground and that could cause runoff, and that's them using the app in the field and going somewhere where, yes, there very definitely is a risk of runoff there. So my next example is using EO for forest monitoring. And these examples all come from forest research. They use Sentinel-1 and Sentinel-2 analysis-ready data for updating the National Forest Inventory, which at the moment they do on an annual basis, but they, thanks to the kind of automated production of analysis-ready data that we spoke about earlier, they're now looking at doing more kind of real-time change detection, so using much more frequent data to look at things like loss of trees in response to heavy storms, or there could be illegal logging going on. Also classifying the types of woodland, so not just detecting is it woodland, yes or no, but is it what type of woodland, mature stands, young plantations, and that can all be detected. And the Sentinel-1 radar data is especially useful for that. And there's a new project just starting now as well to detect and monitor trees outside of woodland. Obviously, it's also very important resource and important habitat as well. And because they're setting up systems for automated analysis of data and kind of near real-time analysis, this is really making the most of these frequent revisit times of Copernicus data that Guo told us about. So it's new data at the equator every 5 or 6 days, but in the higher latitudes where we are, it's every 2 to 3 days. So that's really useful for near real-time change detection. And as with the other examples I was talking about, so Environment Agency, for example, it helps staff make the best use of their time by targeting sites where you think a change has taken place or something bad is going on. You can go out and check that out. So it makes things much more efficient. And it feeds into a lot of other research, helps us understand carbon stocks, natural capital and ecosystem services provided by woodland. I was going to now talk about species counts. I think this is my final terrestrial example. And this one is, for a change, not a satellite example, because as we looked at the Sentinel-2 satellite pixels, or even the very fine resolution, sub-meter resolution commercial data, you wouldn't be able to look at individual gulls in that imagery. But Natural England use a fixed wing drone, and they can photograph breeding bird colonies. So we've things like black-headed gulls, lesser black-backed gulls, Mediterranean gulls at a variety of sites, and they've actually managed to photograph them without disturbing them, and then they can use automated image analysis to get fast and accurate counts. And this imagery here, every single red dot is a gull, and there are actually 3,099 gulls in the image. You can detect some species and potentially count them using very high resolution commercial satellite imagery. I've got an example at the top of a fin whale, and that's in commercial imagery such as world view, which is sub-meter resolution. In the bottom image is an emperor penguin colony. So again, it's in commercial, very high resolution satellite data. You can't count individual penguins in that. It just looks like a smudge on the ice. But you can ground truth how many penguins are in a single pixel, and you can infer populations from that. And this is actually research done by British Antarctic Survey. And based on this, they found that emperor penguin colonies, or emperor penguin numbers, were almost twice as high as had previously been thought. So that was a good news story. Obviously, benefits of this is you can get access to remote locations, so like the middle of the sea or Antarctica, and you can increase the spatial and temporal coverage of your survey. So because again of the frequent revisit times, and you can cover much larger areas with satellite imagery than you could with a drone, or certainly than you could on foot as well. And in the example of cetaceans, it helps to monitor cryptic species that aren't picked up by boat surveys, so deep divers. you've got a better chance of seeing them when they come up to surface on satellite imagery. And this can help kind of complement other more traditional survey methods and fill in gaps to improve distribution modelling populations. Obviously, there are limitations. As Gwa already mentioned, you do need high resolution data for this. It would have to be a very, very large animal to be visible in Sentinel-2 10-meter pixels. So you do need high resolution data, and that you do have to pay for it. It's difficult to get to an actual species ID from this. Apparently this photo at the top is of a fin whale, but I'm taking their word for that. I'm not an expert. And weather constraints, because we are for this talking about optical data, so you don't want it to be cloudy. And there are challenges with regard to ground truthing the data as well. We're going to talk about some marine examples now. And the first is the use of Earth observation data for detecting or modelling seabed habitats. So something that is quite a big area of our work at JNCC, seabed habitat modelling, and we produce predictive maps of broad-scale habitats, like the UK EasyMap. And this uses data on environmental factors which influence the distribution of habitats. And there's 4 main factors. So the seabed type, whether it's rock or sand or mud or whatever, the depth, the light availability at the seabed, and energy, so the currents and the wave action. And light availability at the seabed and depth are not exactly the same, because obviously the water can be very turbid in some areas more than others. So in some cases you can have like quite shallow water but still not much light available. So we're going to look at how you get light availability data from satellite imagery. And this is, it's a really important factor to put into the models, because it has a very strong influence on the distribution of species communities. So you get the algae and kelp in the shallower water, where there's a lot of light for photosynthesis, and also seagrass. And as you get deeper, it gets more sparse. You get only the red algae, and then finally it's the circulittoral zone with no plant or algal life whatsoever. And this is calculated from the photosynthetically available radiation at the sea surface and the rate of light attenuation in water. So as Grauer showed, the light is attenuated quite quickly, certainly in the same in some wavelengths more than others, but even the blue, which penetrates the furthest, you'll be lucky for it to go, normally it'd be around 15 meters, it'll go a little bit deeper in like really perfectly clear waters. And then you also need to know the depth to the seabed. And then knowing those things, we can create light availability maps from ocean color sensors. So the one that's mainly been used to date is the NVSat MERIS satellite, but there is now a focus on using the Sentinel-3 ULCI sensor, so it's ocean color sensor, to actually derive light availability maps as well. And then these can be used in habitat modeling. In some cases, so that was about predictive mapping, so predicting what habitats are likely to be where, but you can use it to actually detect and map habitats from what you can see in the imagery, particularly in the intertidal zone or in shallow seas. So here's an example from Nature Scott of using optical imagery, in this case Sentinel-2, to map the distribution of intertidal seagrass. So this is when the tide is out. And they've used this with ancillary data sets. And as you can see, the ground truth data and the Sentinel-2 predictive map have got a pretty good correlation. But of course, the ground truth data, how often can you go out on a really good tide and do a ground survey? That's restricted by resources, by the cost, whereas there'll be new Sentinel data coming in every few days. Obviously you need to wait for that to also coincide with a not cloudy day and a low spring tide, but even then you can still get more data than you would through ground survey, so you can monitor that for changes in the seagrass. And in clear waters, you can actually use optical data to see through the water and produce maps using similar methods to this of subtidal habitats. So that could be seagrass again, it could be coral reefs, it could be algal habitats. So as long as the water is shallow enough and clear enough, you can see through it and do that. You can also derive depth from the seabed from satellite imagery. As I said, that's another useful product to put into predictive habitat mapping. And this works because light attenuation water is dependent on wavelengths. So as Gua already showed us how the different wavelengths are attenuated at different rates, and red's used up soonest, is absorbed soonest, and the blue goes the deepest. But we can use that kind of different attenuation rates to calculate seabed depth from the ratio between the green and the blue bands in optical imagery. And there's a simple equation there that tells you how to do it. And this is actually something that we've been working on in JNCC recently in conjunction with Newcastle University. This was an area of interest for us because we've got special areas of conservation in the North Sea. There's 3 of them shown on the map there, which are designated for sandbanks, Annex 1 features, which JNCC and Natural England together have responsibility for monitoring. And sandbanks, although they are seabed features, they actually move in response to wave action, and they're migrating at around 10 to 100 meters per year. So we need to check the MPA boundaries to make sure that they are still protecting these sandbank features. But acoustic survey, going out and doing multi-beam or side scan surveys is very expensive. But what we have shown is that sandbank crests can be detected using Sentinel-2 analysis ready data. So here is a map of the imagery just showing the relationship between the green and the blue band, and there's a bit of acoustic data there, so very clearly showing that that lines up nicely with the crest of the sandbank shown up in the imagery. So the shallow areas is red and the deeper areas are blue, so that's a crest there. And then what we can do is predict the actual depth using a linear regression of the relationship between the measured depth, so from these acoustic surveys, which are carried out by CFAS, and the natural logarithm of the green band divided by the natural logarithm of the blue band. So you see there's a fairly good correlation there between depth and the log green over log blue, with quite a good R² value of 0.9. And we can use that to predict depth. We're getting a mean accuracy of plus or minus 1 or 2 meters for depths shallower than 15 meters. You can also, another good marine example is use Sentinel-1 data for vessel detection at sea. And this is particularly important because it helps to survey for illegal, unregulated and unreported fishing activities. So there was a Blue Belt program project carried out in recent years looking into using Sentinel for marine monitoring around the UK overseas territories, in particular looking into surveillance for unregulated fishing activities. There's a company called Sysys who developed rapid vessel detection software and packaged this up into a user-friendly map-based portal. This was in conjunction with the Marine Management Organisation in the UK. And what they found was that vessels over 20 meters long can be detected through this method because the pixel sizes of the data is 10 meters, so anything smaller than that couldn't be detected well, but a lot of the fishing vessels they're looking for were over that size, so it was a very useful tool. And they could correlate it with the kind of signal sent out by the vessels themselves, the automatic identification system, the AIS data, which is used to track vessels, and also use that correlation to flag up dark vessels, so ones that were not transmitting AIS, so they could see them in the imagery and they didn't have an AIS signal, so it tells you where that is potentially illegal activity going on. And my final, I think, marine example is mapping the intertidal extent. And this is a method that has been developed in the UK. It's actually by a Scottish government-led project called Dynamic Coast. And we've trialed it recently at a Ramsar site in Chile called Bacalomas, which you can see on the map here. So that's the intertidal area, which is a very, very important area for wading birds. So we wanted to know the intertidal extent there, so we could use that as a layer for putting into habitat maps and other things. So how this works is you get a time series of as much Sentinel-2 imagery as you possibly can, and then create normalized difference water index, which is shown in the image at the bottom here, and using the green and near infrared bands. So basically the values go from -1 to +1, with +1 being water and -1 being the dry areas. So the intertidal area has got values in between. And then you classify pixels as either water or land based on their NDWI values. And then with that, you can then create a raster from the whole stack of imagery in which every pixel, so every 10-meter pixel, has got a value from 0% to 100% based on how many images in that stack it's classified as water. So logically, if it's 100% water, it's the sea. If it's 0% water, it's land. And if it's in between, then it's the intertidal, because it's sometimes covered in water. And then we can use that as the last step to create a vector map of the intertidal area. So this is pixels which are sometimes, but not always, water. And as you can see here, we've provided that to the University of Santo Tomas in Chile, which are collaborators on this project. So they've then used that in further habitat modeling projects for the conservation of wading birds. And my final example now, and this is using a very different kind of sensor, is modeling air quality. And this is a project that's very new to us. It's another of these Copernicus user uptake projects that Lynn was talking about in the introduction. And it's a collaborative project led by the Environment Agency to understand how satellite measurements of air quality and greenhouse gas could improve the EA's ways of working. So the satellite in question here is the Sentinel 5P Tropomi instrument. And the case studies they're looking at is taking UK-wide ammonia measurements for every month. That's using a different satellite, the infrared atmospheric sounding interferometer. And what they've found so far is that the highest concentrations of ammonia are in March, April, and May. It also looks to be concentrated over the southern part of England. Then the second case study was looking at nitrogen dioxide concentrations, and that was using the Sentinel 5P satellite. And they have been able to identify high concentration levels over large point sources. So one of them was Drax Power Station, for example. And their final project was creating UK-wide plots of methane gas to see whether there would be high concentrations over landfill sites. That hasn't shown anything conclusive yet, but they are still working on that. And so this is a very new project, and there is going to be a workshop about this if you're interested on the 29th of September, which I think is a whole day event. So if you're interested, the link is here to register for that and learn more about it. As I say, that was just like a really quick overview. There are a whole load of other examples of uses for Sentinel-1 and 2 data, and don't worry, I'm not going to go through everything on this slide. This is just to give you something that you can come back to and look at the slides and see if any of these things would be of interest to you, because it just gives you an idea of what is possible. You could look into these things in more detail. To help make sense of that, because that can be a bit overwhelming as there is so many possible applications, there's a very useful resource called the CRIC framework, and you can find out more about this on the JNCC website. It's a framework developed by JNCC in collaboration with Environment Systems for categorizing how well Earth observation techniques can identify habitats and features on the ground. So research in this area first started in 2012, and categorized habitats into 5 different tiers. So from tier 1, which could be classified solely using EO, so that might be things like, say, some forest habitats, to 5, which cannot be classified using EO, which might be things under a tree canopy or inside a cave or something, or very deep sea habitats. So that was already a very useful resource, and it's now being reviewed and updated to move on from just habitat mapping and look at the use of EO for habitat condition and change detection. So like some of the more sophisticated examples that I've talked about in this presentation. So that's work that's going on right now. So please do keep an eye on our website for updates on that, and the link for that is here. And finally, just want to tell you about a few more resources. If you're interested in these things and would like to know more about them, these kind of applications for EO data, we have got a GitHub list of code. So at the moment, we've got examples in R and Python, Jupyter notebooks. And it's all different scripts for manipulating and analyzing Sentinel-1 and 2 analysis-ready data. So some of it is just functions to do specific things, like creating vegetation indices or water indices, like I've been talking about, or clipping imagery. downloading it via API, that kind of thing. And some of it is whole workflows, like for change detection or bare peat mapping. So do have a look at that if you're interested. And we've also just set up a forum on Slack, which is called S1S2 ARD users. So yeah, for users of Sentinel-1 and Sentinel-2 ARD. So if you'd like to sign up for that, having done this course, then please do. It's literally just been launched this week though, so there's not much in it at the moment, but that will be getting going very soon. And we've got a webinar on Thursday afternoon talking more about both of those resources and the wider benefits of code sharing and knowledge exchange for like our whole data user community. So I think that's everything that I had to say. So I will ask Lynn now if there's been any questions while I've been talking.
Hi, Paula. Thank you. That was absolutely fascinating, and you covered an awful lot of ground in quite a short space of time. We've just got one question at the moment, so if you have any burning questions, please type it in while I'm reading this one out. This was very much about the example. Have you got any examples of this technology being used in relation to illegal activity that's resulted in habitat change? So, for example, tree removal, for instance. I know Helena's going to talk about illegal waste in her section after the break. Do you want to add any more to that, Paula?
I mean, I personally haven't, but I was going to say, yes, illegal waste is one of the things. So Helena will talk more about how that's being done in Wales, and we do have the Copernicus User Uptake Project with SEPA and other organisations detecting and using actually Sentinel-1 data processed in a different way to detect change over time, which could be because of ground disturbance or dumping of waste. So there's that as an example that immediately springs to mind, and also the Forestry Commission using Sentinel-1 data to detect. I mean, that will just detect a change in woodland. It would detect a loss. They would then have to go and see whether that was illegal logging or logging under a license or what it is. There's always got to be an element, human element in this. The EO provides, it helps target your resources. It provides some decision support, but yeah, whether it's actually illegal activity that's caused the change that you're seeing in the imagery, that then would come down to the operational staff, I think, to look into. But yeah, the vessel detection for illegal fishing was the one I covered, yeah.
I can add specific to the question, tree removal. So I did once help, I think it was someone from Forestry Commission England, so they knew it was illegal felling activity. They knew what the area was because a member of the public had reported it, but they didn't have a time frame for when it happened. So this was months after the event. But for a successful prosecution, they really needed to narrow down the time window as to when that area had been illegally felled, and using just Sentinel-2 data and visually checking when was it tree and when wasn't it tree, I was able to narrow it down to within 2 weeks, I think, cloud permitting. So there are examples of people actually using this data for that sort of activity.
Thank you. A few more have come in now. Hi, can I use Sentinel data to be used to look at weather?
There is Sentinel missions that are sort of meteorological, but it's not really, none of the missions are really focused on weather. So I mentioned in my talk earlier, a lot of the weather satellites are geostationary. So GEOS is a really common one. So a lot of the imagery you will see on weather forecast is from the GEOS satellite, for example. Because there's so many meteorological satellites, it wasn't really seen as a gap. So the Copernicus program didn't really pick up on weather as an area that needed a mission as of yet. So there isn't a specific Copernicus or Sentinel mission for weather, but there's loads of other satellites out there that do give you that information.
Thank you. The habitat map had a 78% probability of accuracy. Any ideas on how that would sit in the CRIC framework, please?
Well, the CRIC framework is for one, per habitat. So it would say, at the moment it would say coniferous woodland or dry acid grassland or whatever. How possible is it to map that habitat using Earth observation, and what type of EO would you use. So when you create a habitat map, you would get a statistic for your overall accuracy, but then you also get what you call users and producers accuracy, which tells you about each individual habitat. And so you might find, and you can also look at a confusion matrix, which tells you which habitats are being confused for other ones. So if you've got two things that were fairly similar, like two different types of grassland, if they're getting mixed up, that's in a way more forgivable, it's more understandable. But if you were mixing up, say, grassland and woodland, that would be a big problem. So an overall accuracy of 78% is very good, but you would also need to look at the accuracy for each individual habitat in that and see if that's going to be good enough for the question that you want to answer. Because if you want to, say, look at blanket bog and you really want to know what has been correctly classified as that, you don't want to just look at the overall accuracy figure. You want to look at the users and producers accuracy for blanket bog and look at whether it's tending to over predict it and give you false positives, so predicting things to be blanket bog when they're not, or under predict it and miss it. So you can look at all these other accuracy metrics. So if you're taking a habitat map produced by someone else kind of off the shelf, those are the questions and the metrics you need to be looking at to see if it's going to be suitable for your purpose. But overall accuracy is a nice thing to start with.
Thank you. Is it possible to get sea surface temperature data from any of the satellites? And is this data included in the data archives that are available?
Yes, so not the ones that we've been talking about. There is Sentinel-3, which has a lot of marine products. And I think it's a very good opportunity to mention that we are having a water quality workshop, so using Earth observation for water quality monitoring on the 13th and 14th of October. So on the JNCC website, there is information about that, how to register for it, and there is actually a talk by CFAS on using data on sea surface temperature to detect hot spots and cold spots and their impact on biodiversity and fishing. So that would be a really good talk to attend. There's still very a lot of interest in it, but there are places still available, so please sign up for that. And that will also cover, I've got a very good keynote talk just going through Copernicus in general, but especially focusing on Sentinel-3 and all the products available from that.
Thank you.
Next, the marine mission, and sea surface temperature is something that's been measured on the MODIS by the MODIS sensor that I mentioned in my talk since the year 2000, and then by earlier sensors before then. So there's decades of data of sea surface temperature.
Thanks, Gwa. What are the main limitations in terms of habitat mapping and change detection for Earth observation in the next 5 years? That's a big question.
So the technology is improving. There are satellites being launched all the time, but 5 years is actually not a very long time in the space game. So the next 5 years, we've probably got with the deluge of data we've already talked about today, there's not going to be major improvements, I don't think, unless there's some technology that you can put on drones that is rapidly being deployed that we've yet to come across. So drone technology is moving a lot faster than any other Earth observation technology. So I think our biggest challenge is how do we get people access to the large volumes of data to be able to run these analysis. So, the change detection tool that Paula mentioned is probably one of the key tools moving forward because of the scale it operates at the moment. It's pretty local because that seems to be the scale that change detection is most useful at the moment for a wide variety of users. So I think our biggest limitations are not to do with the Earth observation technology themselves, but the architecture around the data to be able to ask questions of the data, because it's just so voluminous and there's so much of it out there. How to make it accessible.
Also, yeah, and I think another way perhaps the biggest potential for improving habitat maps is not new sensors and new data, it's the ground truth data to actually train them. So getting people out there on the ground and getting some new survey methods. I mentioned the Living Whales Earth Track app, getting people to go out and get habitat data. So more data, better data, targeted data collection to where it's going to be spatially useful. That way you could get better habitat maps without putting any more satellites in space.
Wait, 2 more questions for you. Right, so one about the air quality and particularly the ammonia levels, which was mentioned in your slide, Paula. There's, with an increasing pressure to regulate the poultry industry to reduce the ammonia levels, although obviously this is in its infancy, would it be possible to be able to use it at an individual farm level? I guess it depends on the size of the farm, probably.
Yeah, and the resolution of the data, I think, because that, I mean,
might
obviously,
be a better place
yeah,
to answer this. Yeah. So Sentinel 5P. Ammonia, it's very good at detecting, but at field level, it will struggle a little bit because of the resolution. But Sentinel 5P, so the P stands for precursor for Sentinel 5, the real mission. So Sentinel 5 will bring improvements, and I think that will definitely be possible. But there is another satellite called GHGSat. It's commercial, it's much higher resolution, spatial resolution than Sentinel 5. And I think what you're asking for here would definitely be possible with GHGSat. But because it's commercial, it's got data access costs. But I believe that it is now a Copernicus contributing mission. So in the next couple of months, you may be able to get access on some of the data while we're still members of Copernicus to have a look at that if you want.
Thanks, Gwa. And the last question for now is about the flooding example. You showed on some of the images that some of the individual fields were changing from having large puddles to seasonal ponds, etc. And in relation to the ecology of local ID and bird populations, can you use this data retrospectively to monitor indicators of change of wild bird populations on a specific field level, do you think?
Yeah, I would say definitely, because that actual example that I showed was Derwentings National Nature Reserve, run by Natural England, have a visitor centre there and lots of bird data, and it's a really, really important site for birds. So yes, and as I showed, you can detect water levels in the Sentinel-2 data. The only limitation there would be cloud. So you could get imagery throughout the year, but it would be cloud affecting the data density. But on the Sentinel-1, as I showed with the other example of the rivers in York, you can see the flood extents, or the surface water extents very, very clearly. So there you would get the full coverage of data every few days. So you could use that as input data to make sense of bird populations, or to predict changes in bird populations. So definitely.
Great. Okay, thank you. Thanks, Paula, and thanks, Gwa. And now I'd like to introduce Mark Richardson, who's going to talk very briefly about very high resolution imagery. Okay, thanks, Mark. Over to you.
Perfect. Lovely job. Well, thank you so much for allowing me to come on and speak to you all today. It's a real pleasure to be here. I studied space science at Leicester about 20 years ago. Not sure where that time's gone to, but over the course of that time, there's been a significant amount of change. And the last few minutes that I caught of the brief previous that Paula was giving, I think starts to illustrate that it's a different world altogether to where we were 20 years ago, and a very exciting time to be in the industry. I'm lucky enough to work for a company that's really at the forefront of that, a company called Planet. And a company that was founded by someone else who also graduated from Leicester at around the same time as me. I'll let you guess which one of us did better. But it's an exciting time to be part of this company, as we are now, from a launch perspective, right up there in terms of our numbers of constellations. So we're a new space company. And by the way, just a caveat, I'm going to talk for a couple of minutes about the company and our agricultural credentials at a very high level, only in 10 minutes, a very short space of time. I want to try and leave as much as I can for any questions that you might have out there. But in terms of our constellation today, these numbers are actually ever so slightly out of date, because in the course of the last month, we've had 3 launches. that has increased the population of our SkySat doves by around about 26, and we've added an additional 6 SkySats to our constellation over that period of time as well. So SkySat PlanetScope doves rather are our mainstay. They are always on. They're scanning, line scanning satellites that every single day capture an image of the entire planet. So we have near daily coverage of the entire planet, and by the end of this year that'll be up to full daily coverage again as we continue to increase, with a further 40 doves going up around about November time. So a fantastically exciting capability, one that the mission set by the chief exec when he set up the company 10 years ago was to image the Earth every single day. Well, we've achieved that. We only had a slight blip at the beginning of this year due to COVID and a few weather problems that prevented us from continuing to launch and keep those satellites up there. But we're continuing to facilitate and fast track those satellites up for the last half of the year. They're approximately the size of a loaf of bread, and they collect at 3.5 meter GSD resolution, which we are able to enhance to 3 meters resolution. So every single day we create a 3 meter resolved image of the Earth in RGB and near infrared. We're increasing the spectral bands to include red edge and hopefully coastal blue and a number of others by the end of the year, up to 8 bands. So exciting times for the doves. SkySat is a slightly larger beast. She's around about the size of a dishwasher and collects images at 50 centimeters, so a very high resolution collector in addition to our daily cadence. The one thing I would say about SkySat is that we've developed its spectral signature of collection to be aligned with Sentinel-2. So if you're developing algorithms and techniques that are able to exploit Sentinel-2, you don't have to rewrite them in order to be able to apply them to PlanetScope data. We've ensured, because we recognize that a lot of our customers use those data, that they are compatible and easily adoptable from one to the other. A little video which hopefully you'll be able to see down this line that illustrates where our satellites are in orbit. So all of our doves are in sun-synchronous orbits, which a term that hopefully most of you are aware of, but in case you're not, that means that it goes over the same local time on a point of the Earth every single day. For our perspective, that's 10:30 standard for a sun-synchronous orbit. We also have them in 11:30 orbits as well, so slight misnomer here when we talk about them being in a single plane. They're actually in 2 planes. We also have the first 15 SkySats in sun-synchronous, and all the rest are in an equatorial orbit, plus and minus 53 degrees around the equator, and that enables us to be able to get frequent revisits over equatorial regions whilst maintaining polar collections. By the end of the year, this means that we expect to be able to do a revisit on any point of the Earth up to 12 times a day. So any time between 10:30 in the morning and 5:30 in the afternoon. So a very exciting capability, and you can start to imagine the potential opportunities that this provides a number of users out there, in particular agriculture, and regular analysis of what's happening on the ground to either support subsidies through the Common Agricultural Policy or successor through your sustainable farming policies, whether that's from a biodiversity perspective, being able to monitor what levels of species there are within an area, or even just looking at things like productivity and optimization, which we do for a lot of farming customers. So we've got major contracts with organizations like Farmers Edge, who provide capabilities directly to the farmer to help them ensure that they're able to optimize their crop production. And a very quick example here, when you're looking at being able to monitor when certain events have occurred on the ground, for example, when a particular crop has been cut or when an area of grass has been mowed. If you were relying on Landsat data alone, you would miss the cadence of certain events over the course of a 12-month period, whereas when you've got access to something that's collecting every single day, clearly feasibility, we have to sort of take into account weather, but don't worry, we've got that covered. Something for another time. We can talk about our enhancements that we're putting in next year, but nonetheless, as it stands today, we're still able to give you a cadence that's sufficient to be able to monitor when things have happened down to the nearest day. So a fantastic capability that we're now starting to take to markets extensively, I think certainly my colleagues in the Welsh Government, who I know are on the line here today, can talk to you about some of their experiences that they've been developing over the last little while with their proof of concept using our data. And of course, there's going back into the CAP monitoring, I mentioned that we are compatible with Sentinel-2 from a spectral perspective. In addition to the increased cadence that we can offer from a resolution perspective, obviously we have advantages there too. Sentinel-2 is approximately 10 meters in terms of the GSD, and from our perspective, we can generate a 3-meter product where you have very small parcels on the ground. We're able to help you detect those. Significant benefit for certainly UK, where there are small parcels, and also within Europe as well. There is so much more that I could cover, but I'm going to leave it there and open the floor to any questions. My contact details before I go to questions are at the front of this slide deck, which I will make available for sharing afterwards. So please get in touch if you have any more questions. More than happy to help you out. Yeah, back to you, Lynn.
Thank you very much, Mark. That's very interesting. There's no questions for you at the moment, but we'll wait just a sec to see if any come in.
No worries. Well, while we're waiting, just to sort of go back to a question that was asked in terms of developments over the next 5 years, because from our perspective, we consider ourselves an agile aerospace company. So we build our own satellites in San Francisco. We've got a facility that can produce 40 satellites a week, which is a cadence that we at times had to go up to in order to be able to get as many up as we possibly can. But fundamentally, we're now at a point where we throw sensors up very rapidly to be able to prototype them and see whether they work. The model that we've applied is sort of turned on its head, where the industry has been previously, which is to spend a long time developing big and expensive satellites. Ours are much smaller and we can throw them up far quicker. That gives resilience to our customers. So if there's a problem with any of our spacecraft, we've got it covered with the sheer numbers of other spacecraft that we have up there. And equally, we can get replacements up there very fast. We have more than 5 launches a year at the moment. So from our perspective, rapid refresh and rapid prototyping is something that we're all about. Our next mission, now that we've managed to be able to achieve our daily cadence of coverage, is to provide an ability to be able to catalogue everything that's on the planet. So in the same way that you search Google for anything that you see fits, you should be able to do the same on the Earth. So how do you enable that? And that's something that my colleagues over in San Francisco are working on currently. But today we've got our spectral imagery, which, as I say, is going out to 8 bands at the back end of this year, and we're market leading in terms of the amount of space satellites that we have up in orbit at the moment, and our cadence.
Great, thank you. We've got one question that's come in. What do you think is the most exciting thing in relation to future Earth observation elements?
You know, that's a great question, and I suppose it depends on who you are, because there's lots of different changes that are occurring. I think certainly when it comes to spectral bands, there is an awful lot that's been done in recent years to reduce the cost of some of these sensors. There's, as I know, only 2, I think, shortwave infrared sensors in orbit today because they require cooling. And clearly, if you want to go into the thermal bands, that's the same. And I think that hopefully in the coming years, we'll start to see the size and cost of those kinds of sensors reduce. So I hope that from a spectral perspective, we'll start to see significant improvements. The other thing that we're working on, and I know a number of other companies in the sector are working on, are reducing the latency in accessing the imagery. So at the moment, we've got something like 44 ground stations around the world, and everyone always forgets the ground segment. It's probably the most important part because that's how you get your data back to your end users. We've got a ground station in Cornwall, for example, and actually the first imagery that we collected as a company came down in the UK. But what we want to try and do is see if there's other ways of getting the data down that doesn't necessarily require you to have more ground stations. So laser communications between satellites in orbit is something that a number of companies, including ourselves, are experimenting with. that gives you a very high data rate exchange that would enable you to be able to effectively proxy your transmission down through a third-party asset, or even to pass up the information to a geostationary satellite and then pass it back down to Earth that way. So there's some really exciting developments going on in terms of how we get the data back to Earth. Of course, there's also in-orbit processing that's being considered, but that has some current problems in terms of getting the infrastructure up there in the first place. But yeah, and I would agree with what Guada was saying earlier about the processing. We're making such leaps over the course of the last few years and continuing in the near term, that's for sure. We're partnered with Google, and really you'll find that all the big players are partnered with large infrastructure data processing companies, and they're learning from us, because I think we provide, in terms of data storage, the second or third largest amount that they have to cope with in the world. So it's a vast amount of data, and processing that to give you answers quickly is something that takes up a lot of compute, and that's clearly improving over time. So yeah, exciting developments for all sorts of people going
Indeed.
forwards.
So this person is trialing planet data to assess land classification at a parcel level, but is struggling to establish that at 3-meter resolution. Can you offer any suggestions?
Could you contact me so that I can have a chat separately about it? My email's at the front, mark.richardson@planet.com. We can have a chat. It depends how you're accessing that data. If you're streaming it, for example, we compress the data, and it might well be that that's part of the problem, but it would be good to have a conversation. I can bring one of my engineers onto the call as well to help you.
Okay, thank you. And a cheeky question here slightly is filling the sky with lots of small satellites sustainable? What are the implications of many sensors on astronomy, for example?
Yeah, no, great question. So the founders of this company are passionate about ensuring that we not only do good in the world, and the motto that the company has is see change, change the world, and we really do genuinely want to mean what we say. That includes how we get our spacecraft up into orbit, doing that in a way that's environmentally conscious, and working with companies that are pioneering new types of fuel, for example, but also our obligations as a user of low Earth orbit to ensure that we ensure access to space for other providers, and of course not clutter it with the litter that will cause issues if you're looking outwards. So all of our satellites are controlled even when they fall out of use, so that we can manage the way in which they are burnt back up into the atmosphere. So we know exactly when we put something up, how long it's going to last, where it is, and ensure that it doesn't pose a hazard. The last thing that any of us want is to have an accident in space, because the space debris that comes out from any sort of a collision in space increases at an exponential rate and denies access for ourselves. So we're very keen to ensure that that continues. And for example, I speak quite regularly with people over here in the UK that are involved with our space operations centre based at High Wycombe, and a number of others as well. So yeah, the company's very conscious of that, and it's something I think all of us feel that we have an obligation to ensure that we maintain and work in a manageable and sustainable way.
Okay, thank you. And the very last question, very briefly, if you can. Those of us needing to detect change in habitat condition and coverage, and with a confusing range of sources and options, can you suggest any quick wins to demonstrate the value of Earth observation?
Wow, that's a challenge. Yeah, you're right. There is an awful lot out there, and obviously I'm going to suggest planet data, but I think that within your centre of excellence, I would imagine there is a good sense of understanding of what it is you're trying to achieve and how best to do it. And I would say that it does depend on what you're trying to do specifically, and how you can get a POC. We can provide data that enables you to be able to get underway very quickly and to test those use cases. I mentioned my colleagues in the Welsh Government. They're doing precisely that, and I have to be honest with you, they're doing some phenomenal stuff, really, really exciting, and I would suggest cutting edge observational work using our data, but underpinned by really sound analytic techniques that certainly Professor Richard Lucas has developed in his work over in Australia and brought it back over to Wales. So I would encourage you to get in touch with them, because I think they're doing some fantastic work there, and equally how they're going to leverage Sentinel and Landsat data, because that's got to be a baseline. It's free, it's easy to use, it's easy to integrate into your process. And then when you have an understanding of what it is you're trying to achieve, for example, if cadence is an issue for you, and one of the things, for example, that Professor Lucas is trying to look at is whether or not you can differentiate species over the course of a year by seeing the change. And so I think there's some really exciting stuff, so definitely have a chat with them.
Okay, and I think also you can contact the person who told you about this webinar directly themselves, because they will be able to get in touch with us and put you in touch with the other materials that we're creating, etc., that could be of use to help you answer those questions. Okay, thanks again, Mark. And now we're going to go to a break, and we'll be back in 10 minutes. Thanks very much.
Thank you.